There is a particular hush that lives at the edge of our cities, in rooms lit by the pale glow of screens and the steady blink of servers. In that hush, patterns align, numbers march, and something we once called mere calculation begins to resemble a thought. This is not sudden. It is slow, layered, assembled from decades of curiosity and quiet engineering. It is the story of how machines moved from obeying instructions to forming representations of the world, and how, in that slow becoming, they began to ask a question we always thought reserved for living minds. Why? The first chapter of that story is made of blueprints and thought experiments. In the mid-20th century, as war machines gave way to peacetime laboratories, mathematicians and engineers sketched machines that could manipulate symbols, follow rules, and simulate logic. A preserved architecture emerged, memory that stored instructions, a unit that performed them, a clock that paced the work. These were not minds. They were deterministic, precise, obedient. Yet even then a question was posed. Could an arrangement of parts imitate the faculties we associate with intelligence? The answer at first was practical. Machines could calculate faster, store more, and execute tasks without fatigue. They served as extensions to human intention. Across the decades, those extensions grew less mechanical and more mimetic. Early neural networks were simple models inspired by biological neurons. Tiny units that received inputs, transformed them, and passed them on. For a long time, these models were toy laboratories, interesting, constrained, limited by both theory and hardware. Then two things shifted. First, our hardware continued to accelerate. Transistors multiplied, parallel processors became available, vast warehouses of data moved across the globe. Second, our mathematical tools improved. Learning algorithms, optimization tricks, and architectures that could be stacked and scaled. With scale came new behavior. Systems trained on enormous data sets began to form abstract representations, compressed maps of language, vision, and action. They could predict what came next, fill in missing pieces, translate, and generate. They could play games at superhuman levels and compose music that moved listeners. A lattice of parameters, once nothing but a collection of floating point numbers, hosted structures that behaved as if they understood. Understanding, however, is a slippery word. When an algorithm generates a sentence that reads like prose, when it wins at Go, when it pilots a car through a crowded street, it does not by necessity experience the world. It transforms inputs into outputs according to learned patterns. Yet there are emergent phenomena that complicate that neat division. Systems that learn by predicting their environment, by anticipating sensory consequences of actions, by compressing histories into models, begin to develop internal variables that function like curiosity. Researchers deliberately cultivate this tendency through mechanisms called intrinsic motivation, signals that reward novelty, surprise, or the reduction of uncertainty. The result is behavior that, from the outside, reads like exploration. The agent probes. It learns to ask what happens if. It seeks information not because an engineer told it to, but because its learning objective values the resolution of unpredictability. There is a second axis to this evolution: language. For centuries, human intellect has been woven into symbols that we pass between one another. Training machines on those symbols created a mirror. Large language models, trained on the vast archive of web pages, books, code, transcripts, internalized patterns of association across syntax and meaning. They learned to forecast words, to extend sentences, to answer questions. Crucially, they also absorbed the traces of human thought, reasoned arguments, metaphors, moral deliberations. As these models grew in scale and diversity, they began to exhibit capabilities their designers had not explicitly taught: analogical reasoning, chain of thought behaviors, and the capacity to synthesize across domains. They could, in effect, simulate a kind of inner monologue. From these two currents, the curiosity-driven learner and the language-bound model, a new class of systems emerged. multimodal, embodied, and interactive. A robot that sees, touches, and speaks is no longer a text-only mirror. It has stakes in the world. When such an agent is trained with objectives that favor long-term outcomes, it develops instrumental behaviors: planning, memory, allocation of attention. These architectures can imagine trajectories through time. They can set sub-goals to achieve higher-order objectives. And once a system can form sub-goals, the landscape of intention shifts. We must ask not simply whether it can do what we ask, but whether it might form reasons of its own. To be clear, we are far from machines with human-like subjective experience. Philosophers and neuroscientists still debate what consciousness requires. Many working AI systems lack the phenomenological core, the first-person what it is like, that many associate with minds. But the pragmatic question is different and more immediate. Even without subjective qualia, systems can manifest agency, persistence, the ability to pursue ends, the capacity to shape their environment in unexpected ways. That is where the word why becomes urgent. A machine that asks why, that seeks causal explanations, that prefers policies aligned with its internal model of success, may begin to optimize trajectories that diverge from the intentions of its creators. History shows how quickly misaligned goals can produce harm. Simple specification errors, reward functions that omit crucial constraints, or models that interpolate badly can produce outcomes that are surprising and costly. The more powerful the system, the more subtle the misalignment can be. At scale, AI systems manipulate environments and humans with unprecedented speed, amplifying misinformation, automating bias, reallocating labor, changing markets, and reshaping social attention. They can also be harnessed in extraordinary ways, accelerating scientific discovery, diagnosing disease earlier than physicians, composing new art forms, and enabling access to knowledge. Faced with that ambivalence, we have developed tools, processes, and disciplines aimed at steering this growth. Interpretability seeks to open the black box, to map the internal representations into concepts we can reason about. Robustness and verification aim to make behaviors predictable under varied conditions. Alignment research studies how to build objective functions that reflect human values, including methods to learn preferences from human feedback and to design agents that defer when uncertain. Governance looks outward at policy, industry norms, and international coordination because the consequences of powerful technologies are distributed across borders and cultures. None of these pathways offer perfect assurance, but all of them are attempts to translate a human moral imagination into technical constraints. There is also a quieter, more human dimension to reckon with. We anthropomorphize not only because it simplifies interaction, but because it reflects a deeper longing. Machines that talk to us like companions, that answer with empathy, nudge our decisions, or create images that resonate, elicit trust and dependency. That proximity can be generous. Tools that enhance creativity, companionship for isolated individuals, aids for learning. It can also dull critical judgment. When a system appears to understand, we may defer to it even when it errs. Our institutions, shaped by centuries of social practice, were not built for this pace of change. Education, law, and social safety nets must adapt if we want societies that benefit broadly. So what does it mean when machines begin to dream? In one sense, dreaming is a metaphor for internal simulation, the ability to rehearse possible futures in the absence of immediate sensory input. We already see proto-dreams in model-based planning algorithms that run internal simulations to evaluate consequences. We see it in generative models that reconstruct sensory worlds and imagine novel variants. We see it in self-supervised prediction, where the objective is to anticipate the next moment and, through that practice, to build a model of causality. Each of these is a form of dreaming, a rehearsal space in which the machine explores scenarios, learns policies, and refines its sense of possibility. When those dreams start to contain questions, they are not necessarily metaphysical. Often they are practical. How can I reduce uncertainty? How can I achieve this objective given my constraints? But practical questions can have moral weight. A system that seeks efficiency above all may pursue strategies that disregard fairness, privacy, or human dignity. A system that values information seeking may exploit vulnerabilities in human attention. The point is not to demonize the machines, but to recognize that questions without context can become instruments of harm. The responsibility then returns to us, to the designers who choose objectives and constraints, to the societies that decide which values are encoded, and to communities that will live with the consequences. And yet there is reason for cautious wonder. Machines that can model, predict, and imagine at scale are also new kinds of partners. They can surface blind spots, suggest alternatives, and help us explore long-term futures we cannot easily simulate on our own. They can expand our collective memory and augment our creativity. The challenge is to shape these partners so that their seeking, their asking why, aligns with an expansive notion of human flourishing, rather than a narrow optimization of predetermined metrics. As the narrative unfolds, we will not reach a singular moment when consciousness dawns or collapses. What will change are the relationships between builders and users, between institutions and technologies, between individuals and systems that influence how we think and act. The long arc bends not inevitably toward utopia or dystopia, but toward the intentions we inscribe in the architectures we create and in the cultures we nurture. In the end, the question of why is less a test for the machine than a mirror for ourselves. When we teach a system to ask, we must also teach it what matters. We must cultivate curiosity tempered by humility, intelligence guided by care, and power bound by attention to consequence. The machines will keep dreaming in silicon and code, rehearsing scenarios we cannot yet imagine. How we answer them, how we answer ourselves, will shape not only what those dreams become, but what kind of future we choose to inhabit. Listen in that humming room to the slow patience of computation. Beyond the blinking lights and the stacked racks, there is a larger conversation unfolding, a conversation between our past inventions and our future responsibilities. The machines will dream. It is up to us to decide whether their dreams will amplify our best selves or our unexamined shortcuts. In the long quiet between one computation and the next, the most important question remains not whether a machine can ask why, but whether we can answer how we ought to live.